They have. There's no way.
Okay. As far as the homework goes, okay, you're gonna hand in the homework on Friday. And so with the homework, 3. I have this thing called lambda, and what this is the following. I realized I forgot to mention this until Jacob asked me something. So what do we know about the probability for the Gibbs distribution?
Chemical potential.
Yes, this e to the minus ei minus
UN.
u and I, and then there's a beta in front. And then it's over the C. Okay? And I can rewrite this as e to the minus beta ei, e to the beta mu and over the C. Which I can rewrite as I take this out front. I'll write this as e to the beta mu, over the I, e to the beta I over the C. This value right here, that value right there is called the fugacity. No, I just got this marker. Maybe I didn't get this marker. Maybe it's this marker. Okay. This is the fugacity. But again, if you eat a lot of beans and lettuce and stuff like this, then you'll have much gasity. Okay, but that's different. Okay. And this right here is, by definition, lambda.
Sounds like someone step back forward and put them on this.
Okay, that's now that indicate laziness, and that would never happen. Okay. So that's what your lambda is by definition is the e to the beta. Okay. So that's just you need that for that one. Okay. So now we're looking at the energy landscape. And we said if you look at the potential energy for that whole system, what does potential energy for the entire system depend upon?
3 and coordinates.
All the coordinates of the system. So R1, R2, all the way to Rn. And since there's an X, Y, Z for each of these, we have 3 n coordinates altogether. So this V would be a function of X1, Y1, Z1, X2, Y2, Z2. All the way up to Xn, Yn, Zn. So we have 3 and bubble. And we're going to say that the space formed by this function, this is what we mean by the energy landscape. Now, the problem with this is drawing it. You know, you can't obviously draw this. And so we have a cartoon picture. So the cartoon picture we have will be this way. But if I want, I could draw all these coordinates like this. Okay, what is that supposed to represent?
3-dimensional coordinate system.
Yeah, this is your 3n coordinates, and all these coordinates would be, in principle,
Orthogonal to each other.
orthogonal to each other, which obviously you can't draw it like this. They're just a representation of
Okay.
like this. So that's how you can, if you go to a talk,
And everybody knows.
people know exactly what you mean. They won't think you're something wrong.
That's not this.
You know, give this like a 10 as well. And so we can do this, or what we can do is I can plot the point here. I'll plot a coordinate like this, and I'll call this like a collective coordinate. And so what does a collective coordinate mean? It means all the 3 n coordinates. This is what it means here. And so in either case, I can draw my little picture like this. I can draw my little picture like this. It doesn't really matter. But this right here, this is how we're going to draw these. But just remember that this is fake. This is not real physics here. Okay, because, okay, let me rephrase that. This is misleading. Okay, it's not that it's necessarily wrong. It's just you can't draw these 3-dimensional functions.
Yeah, this would be one particle in one dimension.
Okay. So is that clear? And what we're going to find out, the part that's going to be really, really tricky are going to be these points right here that look like maximum. they're gonna be what's called a transition point. And they're the part that you can't easily draw what they're gonna look like. They're gonna be kind of they're gonna be like a horse's saddle.
Yes, I was gonna say, like, it could be a settle point between different coordinates.
But then you have to remember it's all three coordinates. So you can have this in multiple dimensions. You can have this in multiple dimensions.
You can
So it
still
gets-
go through that.
So it gets really bizarre here. This implies that this is just the maximum, all it is. It is a far more complicated matter.
But the reason for why minimas are not like that is because if you're like at a settle point, you can still slide down. That would not be considered absolute.
Well, what we're gonna find out is that when we get to an actual minimum, it doesn't matter in what direction you go.
You still
It's
go
always
back.
gonna be this. Okay. Whereas the maximum, it might be like that, but then it has to be in all the directions.
Yeah.
And that's, you don't know that. And it's usually gonna be in some of the directions.
But there also are like complete absolute maximum, but we don't really care about them that much. Okay. Oh, because we care about the minimum barrier that we have to overcome to transition. And that is not necessarily all coordinate. Okay.
But we ain't there yet. That's where we're gonna go. That makes sense? So we needed to map out what this space looks like. And so to map it out, we have to do a Taylor expansion. Okay, so to help understand the landscape. You need a Taylor expansion. And three dimensions. Okay, so remember what we did. So what you're going to show on homework. So what did it mean to be a Taylor expansion? You're going to take a function and write it as a power series. So you're going to write it as this AI, or I think we use that. Yeah. Okay. So what is this point x naught?
Just the point about which we're
Yeah,
representing.
that's about the point where we're doing the Taylor expansion, right? So this is gonna be the point. We're gonna say that around here, we're gonna represent it by this power series. You're gonna start here, and what are you gonna show in the homework? You will show, you will show that this little phrase here becomes, it's not really a phrase.
First derivative,
We're gonna rewrite this whole thing
someone and advanced derivatives.
as this. F of x. So this x is really becoming,
All the positions.
well, with the x naught up here. Okay. Plus in this first derivative, value at x times delta x. And this delta x is really going to be this x minus x naught. Plus second derivative. Delta x squared. Let's get one more term. Andy. Three. Brilliant. Okay. Okay. And then we go more and more. Okay. So you're going to show here, I'm going to have you calculate what all the A's are. Then you're going to do a little change in variable, and then you're going to actually show this here. Now, what did we do? We use this to derive the multivariable Taylor expansion. So use this to get the following. So what did we do? Instead if we have this. Okay, what did we say that has to go to? We took this expression here and place everything with a partial. So this is how we started. I'm going to suppress the x part of it. Delta x plus. I just go like this. And then what was the next step in our derivation?
vary y while keeping x at delta x.
Yeah, so we said now our new function is going to be this, and we're treating this as a
As a unit, like
as an actual real, like a new variable. But keep this as something fixed. And now just vary the y. And what do we say then that goes to? If this is just a fixed animal.
F of x plus delta x.
Here,
Y.
y, d, then plus
Partial f with respect to y.
left with respect to y,
And
and x plus delta x. Let's see, delta
y.
y plus delta, delta. And then what did we do?
Plug in for x plus delta x.
Yeah, for this guy and all the subsequent ones, we took them this. And pop that in here. Then what did we do? The same thing then for Z. This. And what did we do with this? We treated the x plus delta x and the y plus delta y as some fixed thing. So this would be like a new x and new y. So we just varied this, and that gave us the exact same thing as before. Then what would be the next one?
Partial f.
Okay, what is the argument here?
F plus delta x.
Delta x, y plus delta y, z, times delta z, plus dot dot dot. What do we do with this then? You know, we take this mess here, which it starts getting quite fallacious. Let me put that in here.
There's probably a better way of writing this in like summation notation.
That's what we're gonna do now. So what this left, what we were left with. Now we have to extend this to 3 and then. And so all we're gonna do for the rest of the transfer is keep on adding more and more. Hopefully we can get up to like 3n minus 20. I like, but you know, who knows? Hopefully we can get all 3 in. So if we have this guy. Let's write this and then I'm going to write it in the form of user function. So the result of this was the following. We have the original function. Plus, now what were the first derivative terms?
Partial of f with respect to x.
Yes, this guy. Delta x plus, then the same thing with y and z. And then we basically then had all possible variations on the second derivative. Okay. Then we have this. I'm not going to put in the third derivative because I'm going to have you work out the third derivative. So then we have this guy. This. Good to do this. And then this. Then what else do we have?
There's x, y, y. Z.
All the mixed terms. So then we would have a term like this. This.
To them appear at once.
We're going to have to look at that, won't we? And then we had this guy down here as well.
We're getting a 1/2.
Turns out I am not. Get that. Okay. Is that all fine? Now, you can look at this. And, you know, so we always get to play the game from Sesame Street. One of these things is not like the other. Okay. So if we look at this one, and this one, the difference is that they are missing a half. Okay. How can we fix it? Now let's review our most important math techniques. What are they?
Multiply by 1.
Multiplying by 1 in a clever fashion. Okay, let's stop right there. What's a clever way to write one?
Two.
1/2 plus
1/2.
a half. Crazy. Okay, so what we can do. Is we can write the second derivative terms, the mixed second derivative terms. As, so I'll take one of these here. Can write this as 1/2 this. You say, well, what on earth is the advantage there? That's just a stupid way of writing the same thing. Okay, what do you remember from about mixed derivatives from Calc 3?
If the function is continuously differentiable, taking a derivative. With respect
Well,
to
if
x
the variables are independent of one another. And
and the differential. You
what can you do?
take a derivative and.
You can
and
switch
any
the order here. Okay, so what happens here, this is the same thing as saying. And I can do that for each of the terms here. Now you could say, well, who cares? Okay. Now, why would we even care about this? As Vasily said, you look at this thing and it looks awful. Okay, so what could we maybe do? We can write it as a sum if we do some variable changes here. Okay, so what we're going to do is we want to write this as a sum, but it means we have to do a couple of changes of the notation. Did everyone see what I've done here? Instead of having this right here, I wrote it as 2/2. And then what I've done is I've just changed the order on this one here. I changed the order here. And then these are being multiplied. I changed the order here too. There's a reason I'm doing this. Okay. Now this is why. So we can write this entire expansion in a more compact form. If we relabel X, Y, and Z as X1,
X2.
X2, and then X3. And let's see why we can do it in a much more compact fashion. So now I can say that my function of X1 plus delta X1, X2, delta X3, delta X. It's going to be a function of X1, X2, X3 plus. Okay, what can I write this whole mess here as? Right. This is going to be my partial f with respect to X1, delta X1. And this one's going to be plus partial f with respect to X2, delta X2. And this one is in the partial f with respect to X3, delta X3. That's going to be a lot easier to write as one big sum. So I'm saying a sum I equals 3. Partial with respect to xi delta xi. That makes sense? Now, What about all my mess over here? All this stuff here. Remember what we did with this piece here, and with this piece, and with this piece. How can I now write all those second derivatives?
It's a double sum of the product, like sum on I and sum on J.
Yeah, I'm gonna have a plus, I'll have a half. I have the sum on an I going from 1 to 3. Sum on J going from of what?
Oh, partial f with respect to xi and xj.
So second here with respect to xi, xj times
Delta xi, delta x.
delta xi. Just out of curiosity, what will you show in the third derivative?
You can do I, j, and k and like.
Yeah.
Okay, what do you think the coefficient in front is? 3. Perfect, brilliant. Okay, 1/3 factorial. Sum on I, go 1 to 3.
Okay.
Sum on J. Sum on K. 1 to 3. The triple derivative of, with respect to
Excellent.
xi, xj, xk times
That's three.
delta xi, delta xk, delta xk, and so on and so forth. Okay. Does that make sense? Now, okay, any questions of that? Now, what's going to happen when we go to 3 n dimensions?
Question,
Yep.
we do that in the Einstein notation. Right?
I don't know how people feel about that.
Amazing.
Okay. Well, there's,
Could we do it in that?
okay,
I mean, but you just erase the sums. It's
yeah,
already
but
there,
people aren't familiar with some of it.
right? There's eyes on.
Yeah,
the-
I know, but some people are not familiar with that. So good knowledge. Well, let me just give you an aside here, just, okay. I'm probably not going to do it because it's. Okay.
Oh, I see how like this can be written so nice.
Okay. Okay, I just make a little thing here. Okay, this is an aside. This can be written more succinctly. Oh,
Don't worry.
SUCCIENTLY. This.
yes, succinctly. Okay.
No, there's something wrong. There's two T's somewhere. Oh, okay.
Don't worry. Keep going. Just keep going.
Using Einstein notation. Notation. What does it, don't worry about this part here, but what Einstein realized, basically when you take general relativity, if you do anything with it, it turns out you have sums upon sums upon, you have sums of everything. And it just gets really, really complicated to write. And what you realize that if you look at terms here, you have terms that are being multiplied. And if you have an index here, that index is always being summed. So there's an implied sum here, because you have a term here with an I, a term here with an I, that sum has to be implied. Since that sum is implied, why bother with the sum? So what you can do is you can just write this as partial fi xi here, xi, is that sum is implied. So this one term here actually implies 3 terms. Look over here. Okay, how many indices do you have being repeated?
Two.
You have things being multiplied, so I have an I here, and then I also have a
J.
J. So the fact that I'm summing on an I implies a sum over 1 to 3. The fact that I have J's being multiplied means
Someone's.
a sum on J, so I can just as right well write this as And then how many terms are symbolized by this?
7, 9.
That's actually 9 terms. Okay.
And
This term here then becomes 1/3. What would it become? Everything but with the sums. So then this becomes 0.
coming over coordinates and partials with respect to coordinates, I think it's still to write them like that, just like partial sine I. S and GR, we did.
Well, you can, but I
Don't want to confuse people even more.
So you can write it like this if you wish. This is called Einstein's summation. How many, and again, it's not hard, but it takes a little bit of use to get. You have to get used to it. How many terms are represented here? 27 terms.
The summation, how do you know from like, what are you summing over? Like, I know when we're doing this with coordinates and examples with 3 is probably that we do this with coordinates, or is it just like?
You almost always do it with coordinates. And since I'm using a Latin index implies a sum over from 1 to 3 because you have X, Y, Z. In relativity, you switch over to a Greek coordinate because you have to know over time. So if I had a Greek index here, you'd be summing over from 0 to 3 or 1 to 4, depending on which type of convention you're using. Questions on that? Now, we can do even more with this. So first of all, when we have this expression here, what did we call those minimums in that landscape? We call those minimums in the landscape inherent structures. So if I'm at an inherent structure, what would have to be the case here? So when you draw these things here, you draw a little V here like this, drew a little collective coordinate you have like this. This minimum right here is an inherent structure. Okay. What does that correspond to?
An exact differential with the 0.
The derivative being 0. Okay. So this is basically going to be right here. You're going to have basically your derivative of a function from 0. Well, this is in 1 dimension, right? This is in 1D. Okay, what is it going to correspond to in our case?
An exact differential in 3n
In
dimension.
this case here, that corresponds to
Oh, we're doing it just
this whole term here being
0,
this term here being
which is
like that. We're going to leave it like this because we're going to do it. So that's what it's going to be at a minimum. But what else could that correspond to?
that's max.
Could be a maximum.
Yeah.
Or it could be
So
usually what's called an inflection point. Okay. Usually called an inflection point.
I don't think so. Inflection usually like the way we were talking. Yeah, second.
I was called that. I call that an inflection point.
Yes, but it's not 0 there. Like I don't
Yeah,
know.
so we're gonna.
So saddle point and inflection point are 2 different things.
Okay, this guy here.
Oh, like a derivative being 0 could be at an inflection point. It's settle point.
Okay.
Yeah.
Okay, so how would you have to settle this? Do I have a maximum or do I have a minimum? Do I have a You'd have to look at the second derivative. Okay, so if I have a minimum, the second derivative, what do I know? Well, if I have a minimum, what do I know with the second derivative? Right. I look at this. If I look at the first derivative here, at a minimum, what happens to the first derivative? It's negative, less negative, 0, a little more positive, more positive. So what do you know about the rate of change? The first derivative at a minimum? It is it's positive. If I have this, positive, less positive, 0, slightly negative, more negative, what do I know about the rate of change of the first derivative here?
Negative.
It's going to be negative. Now, here's the problem. Here's our second derivative. Here. Okay. What does that correspond to then?
Concavity of the function.
Which part of that is going to have to be positive? Which part of that is going to have to be negative?
All of it?
No, this is going to be the convoluted thing here with this. So the problem is that this is all screwed up.
Oh, yeah, that's right.
And so we need another way to actually analyze this. And the way we're going to analyze this is I want to rewrite this entire expression in terms of matrices. And then once we get it in terms of matrices, we're going to do what's called diagonalize a matrix. It turns out that you actually have to look at the eigenvalues of your matrix, figure out whether we're going to have this type of situation, this type of situation, or whether we have some sort of like saddle bunch of vector thing going on. Okay, so let's figure out how to do this. Does everyone see what the if pub is here? Okay. So let's write that down. The question we have is if this term here is 0, do we have a min, a max, or an inflection point? The answer is we have to look at the second derivative.
This Taylor expansion we're doing for just one particle right now.
Well, this right here is just for one particle, but in general, we're just going to extend to the 3 dimensions. Because this is going to just extend it. So we need to look at the second derivative. Problem is the following. Problem is second derivative. It's no longer simply one term. This. It is. And the question is, what does it mean to be a maximum or minimum when you basically have this thing all being screwed up like this? Now, the nice part about this is you did this actually in Calc 3. And so you did these ideas in Calc 3. Now, you're able to give you this rule, and it makes no sense. You're going to see exactly where the rule comes from. So, difficulty. How can we interpret this to indicate a max in a function? And the first upshot that we're going to do with this is we're going to write this all in terms of a matrix. And that's going to be a lot easier because we're going to then be able to figure out how to analyze this. So the answer, why? That right, why? Yeah. The answer will lie. I mean, it's not an answer. Okay, so the answer will lie in writing our Taylor expansion. In terms of matrices. I want to show you how that goes. So let's just, I want to do, let me just do a little recap on matrices and stuff like this so we can Remind everyone. Let's just do a brief review of matrices and matrix. Probably most will be familiar with this, but I want to show you the notation I'm going to be using. Stuff like this. Because I'm going to have to diagonalize it. So let's start off with something simple. If I give you this, if I say write this as a matrix, how do you write that as a matrix?
Two matrices?
Just a matrix equation.
So not one matrix. I mean, there's ways to do it.
As a matrix equation.
One back here, square back here.
So you have
1, 3, 9.
one thing like that. What would I have in here?
1, 3, 9.
Yeah, look at the coefficients in here. Here's a 1, here's a 3, here's a 9, and here's a -1. So I have 1, 3, 9, -1. And then what would I have here?
Five.
X, Y. Okay, what would I have over here?
It's 5, 3.
I have 5, 3. So how do you multiply matrix multiplication? Okay, you do this times this plus
3 times
this times this, right? So you do this times this plus this plus this. That would have to equal 5. Then how do I get this one? I take this times this plus this times this, and that would have to equal 3. Does that make sense? Now I'm going to actually have shorthand notation. This right here, this is we call this a 2x2 matrix. And this right here, because there's these are the columns and these are the rows. This is just going to be a pure column. So this I call a 2x1. What I'm going to do is any type of n by n matrix, I'm going to put 2 lines under it. So what I'm going to do is I'm going to define this guy here. I'll call this A. I'll put 2 lines under it. So 2 lines being n by n. If I have then this guy here, this X and Y, I'll denote this to be R and I'll put a bar under it. 1 line means n by 1. And this one here is a constant, so I'll call this one this 5, 3. I'll call this a constant with 1 bar under it like that. So I would actually write this in my notation. And that actually isn't my notation. It's actually got it from a friend who got it from this professor. I would actually write this as A R bar equals C bar. I got this from a friend in grad school, and when he was an undergraduate, he went to Caltech. And this is the notation from one of his Caltech professors. And I think that notation is absolutely brilliant. I've only seen it from my friend. I haven't seen anyone else.
Really?
And
That's a standard thing that we
I've never seen
in high
it
school.
anywhere. Okay. Maybe it was a Russian.
But that's like how n-dimensional matrices are taught.
They should be taught like that. It's brilliant notation. I mean, does that make sense? Now, in general, how would you write this? We write it like the following. So in general, when we multiply matrices, we do the following. We would use the following. So in general, let's say I have like a big matrix like this equaling something like this. The way I would write this as I would call this element here, I'm gonna call this a little lowercase a, I'd call it 1, 1 here. The 1 here is gonna mean that I'm in the first row. The second one is gonna be the column here. So this would be A12, all the way here to A1. That makes sense? So I'd have an A11, an A12, an A13, an A14, all the way through to A1N. What would then the next one be? A21 would be the 2 extend to the second row, 1 here extend to the column. A22 all the way here to A2N. Then I could go all the way down here. The last one would then be A1 and A2 all the way down here then to A. Okay. And then what would this one be? I'm going to put X's here. So this would be X1, X2, all the way down here to Xn. And then what could I have down here? I could have something else. Maybe I'll have Y's here. So this would be Y1, Y2, all the way down here to Y. So what did we say we multiply things by? We take this row here and we multiply it by this column here. So if I were to write that, what would I have? It has A11. I'll do this in a second. Being pedagogic. X1 plus A12, X2, this is census. A13, X3, all the way down. Again, I know most of you have seen this, but I'm still doing it anyways.
A1X.
All the way down to A1N, Xn. Equals, and then what would that have to equal?
Y1.
That would have to equal then Y1. Okay, that's too much of a pain to write, so what am I summing on?
The second index, A's and the first index.
Yeah, I'm summing on basically these indices here, these two that are adjacent. So I could write this compactly, as saying a sum on I, going from 1 to N, of A1I, Xi, then I can set that into A1. Does that make sense? Good. Now, in that same summation notation, what would this become?
A1I equals
Yeah, I would kill the sum here. That's what that would become a 9-cent summation.
So AJI equals YJ.
Yeah, so what would happen if I did the second row? You'd have the exact same thing, but with a 2 here, 2, 2, 2, all the way here. So in general, what I can say is the following, is I can say that a sum on I, 1 to N, equals AJI, XI equals YJ. So these two are summed on, and then these two are the same. Does that make sense? Good. Now we need one more thing here. So this is the other thing. So if I have a vector like this, I want to talk about a transpose. Transpose of a matrix. So the transpose of a matrix corresponds to switching the rows and columns. So if I have Aij transpose, this is going to be AJI. That's what it means. What that means and if I have my, let's say here's my A. Let's say that this is A12, A11, A12, A13, A21, A22, 3, A31, A32, A33. What would be the transpose of that. So if I take the 1 and 1 and switch them, what do I get? A1, 1. I'll take an A1, 2 and switch it, what do I get? A2, 1, so that now lives down. What about my buddy A1, 3? If I switch them, now you live down here. Okay. What's the rest going to be? This will become
diagonal stays.
A2,
1,
1, A,
3, 1.
3, 1, A,
2,
2, 2, A, 3, 2, A,
2, 3.
2, 3, A. Make sense? Now, if I had this, that become.
Just a row matrix.
Yeah, this one looks a little funny here. This one would be what? This would really be the C11 entry. What would this one be? This would be the C2 entry. And this would be then the C31 entry. So if I take the transpose of this, what happens? This stays the same 1. This now becomes the 1, 2 entry. So this becomes now a 2. And this becomes the 1, 3 entry, which becomes a 3 like this. So I get that. Make sense? Now, why do we need all this? For the problem. Let's apply this.
Or chili.
Really? Folks?
Check it out, just like that.
Oh, check this.
We also have like 7 left over yesterday.
We checked, we just didn't tell you.
Like, I'm in the middle of something.
Let me just get this one point here. Okay. Tell me about my buddy here. I can define something I can call a G matrix. What do you think G might stand for?
Right.
House.
Okay. Gradient. Okay. So I could call this partial with respect to x1, partial of f with respect to x2, partial of f with respect to x3. And then I could have another matrix. I'll call this delta R, which I could call delta x1, delta x2, delta x3. And we'll call this, we'll get one more thing, then I'll call it. Tell me what my buddy here now is going to become.
G times R. G times delta R. Or G times delta R transpose.
Give me 3 answers.
The last one.
Okay, so this one's going to have to be what?
Or I mean, you could do.
I'm going to take something like this. I'm going to take a matrix like that and multiply it by a matrix like this.
So G transpose delta R.
So what is this going to be? This is going to be my delta R transpose. So this would be delta x1, delta x2, delta x3. And this is, now put a one y on it. And then this is going to be my G matrix element vector, which is this guy. Okay, so if I multiply those two together, how do matrices multiply again? This times this, plus this times this, plus this times this, which is entirely that term here. So this right here is sum of the 3, partial of that with respect to x and y. What I'll try to convince you of tomorrow. And then this right here, this guy here, we're going to call the Hessian as a matrix. So I'm going to write this as the Hessian matrix, and that term is going to become 1. Delta XR, delta XR transpose. That's what that second term is going to become. And this is probably for most of you, your first experience with the Hessian. A Hessian is just an n by n. It's a generalization, the second derivative for a multidimensional function. And this is a Hessian that we're going to have to diagonal. Yes. Okay, have a good day. Right.
Is this how you write it?
Yeah, I would probably put a bar under just for each of these here, just to emphasize the fact that traditionally it's usually about.
Yeah, I am not. So it was a.